Today's in this talk, I will talk about the Dirac-Majorana Neutrino type oscillations, which is can be indices by the wave document. This talk is based on the recent papers and collaborated with the Lin Chazo and Hasong Lee. There are many unknown things in the neutrino physics. For example, the neutrino oscillation parameters like the characteristic octant or the mass difference between the first and the third mass eigenstates are undetermined. And also the CP violating paces in the permanence matrix is still unknown. And we don't know that the absolute mass scale of the neutrino. There are many efforts to measure this, like as a CMB mass bound or Trident beta decay experiment or neutrino last double beta decay is constraint. And many anomalies in the neutrino spectrums, like as reactor neutrinos or atmospheric neutrinos, reported that there are many anomalies and there might be some additional stellar neutrino. And one thing is that unknown in neutrino physics is still that whether neutrino is a Dirac type or Majorana type. If the neutrino is a Dirac type, the neutrino and antineutrinos are different. But if the neutrino is a Majorana type, then the antineutrinos are same with itself. First of all, let's review on the how can we write the Lagrangian for the neutrino mass. There are two kinds of the neutrino mass. The one is a Dirac mass term, which is consists by the Dirac spinor with the left-handed and right-handed counterpart. But the Majorana mass term is consists from the Majorana spinor, which is composed by the one counterpart. And the charge conjugations of the Majorana spinors itself. So there are two mass term, Dirac mass term and the Majorana mass term. And when the Majorana mass term is larger than the Dirac mass term, is called the Majorana limit. And the mass eigenstates are written by the Majorana spinor. In this limit, the system mechanism is the brightest. So the active neutrino mass M nu is proportional to the 1 over the MR, Majorana mass term. So if the Majorana mass term is very large, then it can explain the small neutrino mass naturally. And the Majorana mass term is a lepton number violation term, RMV term, or if we assign the lepton number to the neutrino field and the lepton field. The example of the RMV process is a neutrino last over decay. So in this Majorana limits, such a neutrino last over decays can be occurred. And also the Majorana mass term can provide the leptogenesis to explain the baryon symmetry of the universe. There are two different decay modes of the heavy neutrino, and such a two different decay mode can generalize the asymmetries in the early universe. Conversely, also we can consider the opposite limit. If the Dirac mass term is larger than the Majorana mass term, it is a Cauchy-Dirac limit. In this case, still the neutrino's mass eigenstate is a Majorana spinor, but it behaves like the Dirac spinor. In this limit, the system mechanism is not operated, so the Dirac mass term should be the small to explain the small neutrino mass. And the Majorana mass term is small, so the lepton number violation process is strongly suppressed. So the neutrino last orbital decay does not occur almost. And in this case, the leptogenesis is cannot be associated with the early universe too. We consider if the Majorana mass terms changes in time, then the neutrino type can oscillate between the Cauchy-Dirac type and the Majorana type. We call this the Dirac-Majorana neutrino type oscillation. Such a neutrino type oscillation can be realized if we consider the mass variation scenario. Such a mass variation scenario of the particle is often established by using the wave dark matter, which has oscillating scalar behavior. It has following its mass ranges from the 10 to the minus 20 electron volt to the 30 electron volt. The lower bound comes from the Lyman alpha probabilistic constraints, and the upper bounds coming from the two halves, the longer tubular waves length than the interparticle separations dark matter. And the corresponding periods is picosecond to the east, depending on the wave dark matter mass. If we consider spatial homogeneity around the scalar fields in the expanding universe with apparent double matrix, the equation of the motion for the scalar fields following. And in the present time, Hubble friction terms are extremely small compared to the wave dark matter mass. So the solutions are given by the oscillating scalar fields. If we consider there are interaction between the wave dark matters and the neutrino, then the neutrino mass are varied. There are many several works to research is that such a neutrino mass variations, how there's effects on the neutrino levels oscillations. There are several ways to give the neutrino time oscillation by using the such a mass variation. Because if the light year between the Majorana mass term MR and the Dirac mass term MD are changes, then the types also changes. But for simplicity, we only consider the Majorana mass term only generates from the coupling with the wave dark matter. So the Dirac mass terms arising from the Euclid's interaction, HLM, so Dirac mass terms are fixed by the MD. But Majorana mass terms arise from the wave dark matter's coupling, pi and m. So the Majorana mass term MR becomes a function of the time with the oscillating behavior. And the amplitudes are given by the coupling Z and the oscillation amplitude, which is a function of the wave dark matter's energy density rho pi and the mass m pi. So the Majorana mass terms are oscillating, so that's the MR of the T. So in the light figure, the black curves is the Majorana mass terms with oscillating behavior, but the Dirac mass terms are fixed by the MD. So when if the Majorana mass term MR is smaller than the Dirac mass term MD, then neutrino becomes the Cauchy type. And when the MR equals to exactly 0, then the neutrino type becomes a pure Dirac instantly. And when the Majorana mass terms MR is larger than Dirac mass term MD, then the neutrino becomes the Majorana types again, and the such type oscillations occurs periodically. We consider possible constraints on these fibers regions in the cosmology and the neutrino physics. This is a parameter space for the coupling C, Majorana mass oscillation amplitudes emerges, and the wave dark matters as m pi. The blocks regions that correspond to the lower bounds of the wave dark matter mass, 10 to the minus 20 electron volt, which comes from the Lyman alpha polarizer. And the large region is the inconstant parameter space with the dark matter lyric density. So the wave dark matter density is larger than the local dark matter densities in the galactic halo. And the density line represents that even the wave dark matter is a fraction of the total local dark matter density. There are still remains parameter space. And the yellow regions that correspond to the disfavored regions of type oscillation. We consider coupling is smaller than the one, and the MD equal to the Higgs bound as the conservative limit. So there are still remaining blank regions in the parameter space, which can provide sort of the neutrino type oscillations. And also the neutrino mass variations can affect the neutrino-related physics, like the Flyby oscillation or cosmological observable. For example, the active neutrino mass is given by the system mechanism in the Majorana type, but in the Cauchy-Dirac type, such system mechanism broken. The active neutrino mass is almost generated through with the Dirac mass with a small splitting. So to explain the small neutrino mass with the system mechanism, the Cauchy-Dirac type should be existed in the short time in the total period. So we consider time average analysis. For example, the time average is the active neutrino mass should be less than the mass bound 0.1 electron volt, which comes from the CMB data or three-dimensional decay experiment. So by using this time averages, we found the following constraints in the right figure: the parameter space of the Dirac mass term MD and the oscillation amplitude MRG. The yellow regions are excluded because the time average of the active neutrino mass exceeds the 0.1 electron volt. And the distance line represents the Cauchy-Dirac time right here, star over t, which represents how long the neutrinos existed in the Cauchy-Dirac time in the total period. So in the left upper regions correspond to the Dirac mass is larger than the MRG, and the right side is correspond to the Dirac sum is smaller than the oscillation amplitude, and we can bound that the survives region, this blank regions represents that only the Cauchy-Dirac type should be the shortest time is surviving. So the such a short Cauchy-Dirac type constraints coming from the time averages analysis. So what can we expect is if the neutrino type oscillation occurs? The neutrino last over decay is one example of the Lambda number violation process, and the Lambda number violation process only occurs at manual time. So in the Cauchy-Dirac type, the Lambda number violation does not occur, so the such a neutrino last over decay is strongly surplus. The neutrino last over decay light is given by the following the effective the neutrino mass with the nuclear backtest, enemy backtest. This enemy backtest the functions of the neutrino mass, and we also consider the extended the permanence matrix to include the star neutrinos the contribution. For example, for single flavor case, the one terms that comes from the active neutrinos and other terms comes from the heavy neutrino. And in the Cauchy-Dirac limits, the active neutrino mass and the star neutrino mass is almost degenerate with the small splitting, and also the mixing angles are maximal in the Cauchy-Dirac limits. You can see that is bigger. So the orange line and the brown line correspond to the active neutrino mass and the solar neutrino mass, both the mass eigenstates. In the minor limits, such as some mechanism of varieties, but in the Cauchy-Dirac limits, they are almost degenerates. And also in the Cauchy-Dirac limits, the active solar neutrino mixing, both the left and the right chiral mixing, sine scale theta is almost maximal. So that this is a 1/2. So these two sums are almost cancelled with the precise sign. So the such amplitude A is strongly surplus in the Cauchy-Dirac limit. So if there's a neutrino type oscillations which induces by the wave dark matter, then we can observe the turn on and the turn off behaviors of the neutrino last of double beta decay. The green curves are manual mass term, the oscillates, and if the manual mass terms are smaller than the big Dirac mass term, the neutrino type becomes the Cauchy-Dirac type, and the neutrino last of beta decay just strongly surplus. And we can check the Cauchy-Dirac's time is extremely short in the total period. We consider the following the parameters choice, MD and MR0s. Also, the neutrino type oscillation can provide the modulation behaviors through other process, like as a cosmic neutrino background, which has a different light for the manual mass, manual types and the Dirac type. Finally, also we consider some of the early universe possible phenomena for such neutrino mass variation. In the early universe, the leptogenesis occurs to explain the baryon symmetry of the universe. The baryon symmetry of the universe, the BAU, is parameterized by the eta B, which has order of the 10 to the minus 10. And the standard model cannot explain, so that there are several baryogenesis models. And the leptogenesis is one model of the baryogenesis. The leptogenesis occurs with the decay of the heavy matter neutrinos N is a mass eigenstate here. And there are two different decay modes. N goes to the lepton Higgs or the anti-lepton and anti-Higgs. And from these two different decay modes, the lepton asymmetry is generated, and via the parallel process, the baryon asymmetry is generated. Such lepton asymmetry generations can be parameterized by the CP asymmetry epsilon, which is defined as the difference between the two decay modes with the normalization. And such a CP asymmetry epsilon shapes a scale of the 10 to the minus 6 to gives the observes the BAU. And this decay light is a function of the manual mass scale and the CP bar lighting phases. So the manual mass scale is one important parameter in the leptogenesis. And in our models, the manual mass sums changes over the cosmic history. The oscillation amplitudes are proportional to the roots of the anode density law. And this energy density shows a model-like behaviors in the cosmology. So the monomer mass terms are proportional to the a to the minus derivative as either scaling factor. So we can expect that in the early universe, the monomer mass term is very large. And the extremely very early universe, the Hubble prediction term is very large. So from the equation of the motion for the wave dark matter, the wave dark matter field power is frozen. So if the leptogenesis occurs in such a very large monomer scale, and the neutrino type oscillations occurs in the relatively small monomer mass terms in the present time. There might be the link between the early universe and the present time. We consider the monomer mass terms that fixed in the extremely early universe due to the large reflection term. And the light year between the MR star for the early universe and MR zeros and the presence time is given by the functions of the wave dark matter's mass and pi. For example, the m pi equal to the 10 to the minus 20 electron volt. MR star is almost a GOT scale, but in the present time, MR zero is almost a testable scale with a 10 electron volt. But by using the Casas-Ibarra parametrizations for the Yukawa matrix, the Yukawa matrix is proportional to the current monomer scale. So to keep the largest CP symmetry, because this epsilons related with the scale of the Yukawa matrix, to keeps the inner BIU the inner CP symmetry epsilons are necessary. Because the monomer mass terms in the present time is small, 10 electron volt, so the CP symmetry should be resonantly enhanced by the degenerate mass spectrum. So the points of this slide is the current monomer mass scale is testable, but it requires the resonant leptogenesis scenario. And then maybe I will explain the such leptogenesis with the neutrino mass variations in the next video. This is already the publicist. So in summary, if the ratio between the Dirac and the monomer mass terms changes in the time, then it can provide the Dirac-Majorana Neutrino type oscillation, and this can be realized by using the wave dark method. And there are some several constraints from the cosmology and neutrino physics, and the cultural moment should be short to explain the small neutrino mass. And such a neutrino type oscillation can provide the modulation behaviors like as a neutrino lateral decay. And there are some interesting connection between the early universe and the present time neutrino physics. And such heavy neutrino mass variations can provide the interesting phenomenal losses of the leptogenesis. Okay, thank you for listening. And there are some of the backup slides, but I will just skip about these things. There are some of the Dirac-Majorana spinor formalism. How can we obtain the mass eigensize and the mass eigenvalue from the neutrino mass matrix? And there are some several limits, pure Dirac case, Dirac case, and Majorana's limit. We found the mass eigenvalue of mixing angular mass eigensheight. And there are also some detail about the neutrino lateral decay. We extend the pure matrix, including the nuclear matrix element and factor, which is the functions of having neutrino mass. And there are also some calculation for the neutrino lateral decay amplitude for the single flavor case and the triple flavor case. And there are several explanations for the variant symmetry of the universe and the leptogenesis. There are two scenarios like such just a standard thermal leptogenesis and the resonant leptogenesis.